All right, this is the third part of 4.1, maxima and minima. Question is, when does a function have an absolute maximum and or an absolute minimum? So we just looked at some cases where it doesn't have both of those. And are there any guarantees that we can put on it where it definitely does have an absolute max or an absolute min? So there is. There's a guarantee called the extreme value theorem. And it goes like this. Suppose f, a function, is defined on a closed interval. This is important. Closed interval AB. So closed means including the endpoints. Including the endpoints. If f is something, then f attains an absolute maximum value, f of c, and an absolute minimum value, f of d, at some c and d. So what is this critical property? It's just continuity. If f is continuous, then f attains an absolute max and an absolute min. So that's neat. So continuous functions on a closed interval have an absolute max and an absolute min somewhere. So let's take a look at an example of how a case where this works when it's continuous, and then the opposite case where it's not continuous. Okay, so a continuous function, let's see. So we have our interval a to b, and well, a continuous function can do a lot of things, right? So let's say it does something like that, and well, it attains a local max many times, right? So all of these points are local max points, but this one at the top, that would be the absolute max, and let's call that point C. So the absolute max is at f of c. Maybe I should draw a y-axis here. And where's the absolute min? Again, it attains a local min at many places, right? These are all local min, all these points. But there's only one point that's lower than all the other ones. That would be the absolute minimum at. So here, in that case, D is the same as B. B is D. Absolute min at B. Absolute min f of B at x equals B. Okay, so proving the extreme value theorem is something, we're not going to do that. It requires some deeper theory about what exactly is continuity, what exactly is a number, in fact. And but this just illustrates the basic idea. Okay, what about a discontinuous function? So let's do two cases. One where the function, we'll do one where it doesn't satisfy the conclusion of the theorem. Doesn't satisfy the conclusion. And we'll do one where it does satisfy the conclusion. So when I say doesn't satisfy the conclusion, I mean it doesn't have an absolute max or it doesn't have an absolute min, one of those two things. So let's say this is our a and our b like this. So what would be a discontinuous function that doesn't satisfy it? Well, let's say it has an asymptote like this. That is, and let's say it continues here and it goes like, let's say this. Now, this is my open circle. So I'm making this pretty wild. This function has neither an absolute max or an absolute min. There's no absolute max because of this, because it just goes up and up and up forever, so there's no limit to it. And because of this, there's no absolute minimum either, because it seems to be approaching this point. Let's call this point, I don't know, let's call it m for minimum, the function approaches this minimum m, but doesn't attain it, but doesn't we could say attain that y value. So it doesn't have an absolute min either. Okay, now what about a discontinuous function that does satisfy the conclusion? Well, that's pretty easy. I could just do this. I think we already drew an example like this actually. There we go. So how about that? It's discontinuous, right? Defined everywhere, but it does attain maximum here at the point C, and it does attain a minimum down around there at the point D. So the absolute max is f of C, and the absolute min here is f of D. So the story is complicated. The story is that if it's continuous, then it attains an absolute max and absolute min. But if it's discontinuous, then anything's possible. If it's discontinuous, anything is possible. Okay. So let's do an example. Okay. Let's see here. So we have 3 examples. I think we might actually split this up here. Maybe we'll press on. Let's see. Yeah, we'll press on. Okay, so here's a kind of practical example about water. So the density of water. Between 0 degrees and 30 degrees, the volume of 1 kilogram of water depends on the temperature. So the volume as a function of temperature is this. So notice it's a cubic function. So it's quite a complicated variation here. Find the temperature at which water has its maximum density. So let's think here. What is density? Sometimes it's represented by the symbol rho. Density is mass divided by volume. In this case, it's 1 kilogram divided by V. So that's going to be maximum. So that quantity is at a maximum when V is at a minimum, right? So when is V at a minimum? So what we're going to do is we're going to check the critical points, and we'll check the endpoints. So what are the critical points? That would be where dV dt is 0. So what is dV dt? It's going to be derivative of a constant is 0. The linear term here. The next term is 2 times 0.0085043 minus 234,679t squared, and we want that to be equal to 0. So we can solve for t using the quadratic formula. So minus b plus or minus b squared minus 4ac all over 2a. And I'm actually going to, these numbers are a little tedious, so I'm going to just pause for a second. I'm going to punch in these numbers into the formula, and then I'm going to write down the 2 numbers. We'll see in a moment. All right, so the quadratic formula gives me 2 possibilities. First one is 3.9665 or 79.5317. Just point out that I had to put this t in here too because I forgot to write the t a few seconds ago. So those are the 2 critical points. Now, what about the endpoints? So the endpoints are t equals 0 and t equals 30. So at t equals 0, we get v equals what? If I put in 0, okay, so let me, excuse me, let me clarify something. So we have the 4 possible t's, right? Where where the volume is a minimum. And so now we're going to check the volume for all 4 of those. So if now I'm going to check the volume. So v equals what? I plug in t equals 0, and I just get the constant term, 999.87. And what if I plug in v into that? 30 in, what do I get? Let's see. I'll take a pause here. So at temperature of 30, I get a volume of 1003.76. So that's a larger volume. And then at t equals 3.9665, I get a volume of, so I'm plugging that into the formula. It's a little tedious to punch it all in. 999.74. What about the last one? T equals 79.5317. Well, I'm actually going to neglect that one because it's outside of the 0 to 30 domain. This function is only accurate between 0 and 30. So which one has the minimum volume is this one. That's slightly smaller. So that means that water has a maximum density at 3.9665 degrees Celsius, so about 4 degrees Celsius. And that actually has a huge real-world impact. So if you look at lakes where it's freshwater, the bottom of the lake will usually be at this temperature, 4 degrees, if it's a deep lake, because that's the densest water can be. So if it ever cools down to that level, it's going to sink to the bottom and stay there. Okay, now let's carry on. We've got a couple more examples. So let's see here. Show that 5 is a critical number of this function, but the function does not have a local extreme value. Okay, what is that saying? Show that 5 is a critical number. Let's see, so I have this function, and it's a cubic, and it's shifted. Let's try to sketch it maybe before we do anything else. So if I sketch this, a cubic normally looks something like this, right? And if I shift it to the right by 5 and up by 2, then it's going to look like this. Oops, this gets in the way. So I'm shifting it up by 5 and right by 2. Nope, other way around. Right by 5 and up by 2. So that's the 0.5. So what we're saying is it's a critical value there. And that means that either the derivative is 0 or undefined. It looks like the derivative is 0. Horizontal tangent. Now let's verify that. So g prime of x is 0 plus 3x minus 5 squared times the derivative of the inside, which is 1, right? 3x minus 5 squared. So what that means is, therefore, g prime of 5 is 0. You can see that. If I plug in 0, oh sorry, if I plug in 5, I'll get 0. So that means 5 is a critical number. Now, how do I know it's not a local extreme? Well, let's think about this. If I take a number that's near 5, let's zoom in on the if I zoom in on the graph here, the graph looks something like this, right? So if I zoom in on this piece here, it looks like this. Oops, let me try that again. It's a little bit smaller to the left and larger to the right, right? It's smaller to the left and larger to the right. So I can't, let me try one more time. And so it can't be a maximum because it's not larger than the points on the right, and it can't be a minimum because it's not large, it's not smaller than the points on the left. So it's neither a local max or a local min because g of x is increasing on both sides. On both sides of x equals 5, right? It's increasing up to that point, and then it's increasing again after that point. Okay, so cubics don't necessarily have a local max or local min. In fact, that's true for all odd powers. All odd power functions, they'll have a critical point, but it's not going to be a max or a min. Okay, now last one here. So we're going to look at a more complicated function. It's a quintic, a fifth power. We're going to use a Desmos to graph the function, and then we're going to find the extreme values using calculus. Okay, and that's our last example. Okay, so let's see. Let's make a graph with our favorite graphing website. So y equals 1/5 x to the 5th plus x to the 4th minus 4x cubed minus 3. Okay, so that's a strange graph. We have to zoom out in order to see it properly. Let's see here. So let me make it go from minus 10 to 10. And the y-axis, we can go from, I don't know, minus 20 to 20. Let's see how that looks. It's more, right? We need to go from minus 50 to, let's see, minus 20, minus 40 to 40 maybe. Oops, I forgot the minus sign. Okay, still can't see it all. Let's see, 100? I just can't see the top of the graph. 400? No. 500? 800. There we go. So that's the graph. Kind of captured all the turns. And let's take a screenshot of that. Okay, so now it looks like there is, well, we can see some of the critical points pretty clearly. Let's see here. Okay. So I can see that there must be a local max here, and it looks like maybe around here, but I can't really tell if there's any more. Maybe in here somewhere. Is there anything else in here? So, okay, we're going to find all local extrema. So those local extrema are located at critical points, critical values. The book calls them critical numbers, but I always say critical values. So that's places where the derivative is 0 or the derivative does not exist. Those are the two places to look. So what is the derivative? F prime of x is, let's see, I'll bring down the 5, so that becomes 5 over 5. That's just 1. X to the 4th plus 4x cubed minus 12x squared. And then the 3 becomes 0. So that's the derivative. And before I let it equal 0, I'm going to, let's let it equal 0. I'm going to factor it now. So that becomes x squared plus 4x minus 12. So let's see, can I factor this? Plus 6 minus 2, it looks like. So I have 3 possibilities: x equals 0, or x equals minus 6, or x equals 2. So I can see now that at 2, at x equals 2, it looks like it's a local min, right? You can see that here it's f of 2 is less than f of x for nearby x values. And so that's a local min. And this one is clearly a local max, because let's call that f of minus 6 is greater than f of x for all nearby x's. It's not bigger than these ones over here, but that's not nearby. It's just in, say, like this interval. In this interval, you can see it's clearly greater than all those points. Now, what about 0? It's hard to say. And so let's summarize this. At x equals minus 6, it's a local max. Now, let's make an observation here. So let's try this. So near x equals 0, f prime of x is, which is x squared times x plus 6 times x minus 2, is approximately equal to what? So what I'm going to say is this first one is approximately 0, but that will defeat the purpose here. So I'll leave that as x squared. But these other two, if x is 0, like if x is very close to 0, then this will be close to 6, because the x won't make much difference. And this second factor will be close to minus 2. So that would be approximately the same as negative 12x squared. In other words, which is less than 0. So the function is decreasing near 0. It's strictly decreasing. So it actually looks, if we could zoom in on it, it would look like a cubic function. So it would look like it goes like this and then like this near 0. So decreasing, then it's flat for just a moment, and then it's decreasing again. That's the derivative. So this is so f looks like a cubic there. Near x equals 0. So at 0, there's no local. At 0, it's neither a local max or a local min. So this is kind of I would say a more advanced kind of reasoning, and I hope that you followed it. If you didn't, then maybe ask me about it. But I'm not going to expect you to develop that kind of reasoning your own right now on your own. But nevertheless, that's the truth. That's what the answer is. So what we're saying is that if we could zoom in here, it doesn't have a bump or a valley. It just goes down. It kind of has a step. It flattens out and then it keeps going down. Okay, now last part here. Explain why f has no absolute max or absolute min value. It only has these local ones. Well, the reason is that if you take the limit as x goes to infinity, limit x goes to infinity of f of x is what are these terms? So it's x to the 4 minus 4x cubed minus 3. Well, how do we do this? How do I evaluate the limit? Well, one thing I can do is factor out x to the power of 5 out of all of these things. So what happens is I get 1/5, and this will become 1 over x. This will become 4 over x squared. This becomes 3 over x to the 5th. And I can see that this first factor tends to infinity, plus infinity, and the rest of this goes to 1/5 plus 0 plus 0 plus 0. So I end up with plus infinity, right? So all that's saying is that this first term is all that really matters. So that's called the leading term. So the leading term causes, because it's the highest power, it causes f of x to go to infinity as x goes to infinity. And similarly, as you go to negative infinity, that will become, it's going to be the same thing as limit x goes to negative infinity of x to the 5th, 1/5, 1 over x. And what happens here? Well, x to the power of 5, that's an even power, so it'll be negative, 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 which is negative times 1/5. So that's negative infinity. So it can't have an absolute max or absolute min because it just keeps going larger and larger in both directions. So we say, we see that f has no absolute max or min value since it approaches, maybe instead of it, I'll say since f of x approaches plus or minus infinity in, maybe I'll say this, approaches plus infinity in one direction and negative infinity in the other direction. And why does that mean there's no absolute max? Well, in the other. So that means there's, if an absolute max or min is a specific number that's larger than all the other numbers. How should I put this? An absolute max or min is always a specific number. It's not infinity. So plus or minus infinity doesn't count. It doesn't count as a max or a min. Okay, so we got through the end there. We're going to be using maximum minimum values for later what we call optimization problems. So finding the best or the worst, the cheapest or the most expensive. We're also going to be using the same idea of critical points to help us graph functions. So we'll see you then.